Hello everyone. Today I'm going to present a work that I've developed during my time at the Dynamic Robot Systems group at the University of Oxford. The goal of this work was to enable dynamic locomotion of quadruped robots on non-coplanar surfaces. This imposes the explicit consideration at the motion planning level of the main feasibility constraints of the platform, such as the joint torque limits. In our previous work, we had already developed an intuitive tool for the projection of the joint torque limits into a 2D plane, which can be used to plan the robot center of mass trajectory. We had called this the feasible region because it not only was an extension of the support region to non-coplanar contacts, but it also allowed to understand if the ratio between the body weight and the motor limits was sufficient for the robot to overcome its obstacles. We show here the capabilities of the feasible region to capture the actuation authority of the robot. We apply on the center of mass of the IQ robot a vertical force of increasing amplitude. We can see that the feasible region gets smaller and smaller. At some point, we stop increasing the external force and we have the robot move laterally. As soon as the projection of the center of mass crosses the boundaries of the feasible region, we can see that also one of the joint torque limits is violated, thus proving the one-to-one relationship between the two. Based on the feasible region, we came up with a stability metric that consists of the sign distance between the instantaneous capture point, which is represented by the red dot in this figure, and the edges of the feasible region, the green area. When this distance is positive, it means that the robot is instantaneously stable, in the sense that it can come to a full stop without any extra step. If this distance is negative instead, it means that the robot will need to take at least one extra step to come to a complete stop. The computation of the stability margin according to the analytical approach requires the computation of the feasible region, which is achieved by means of the iterative projection algorithm, and of the capture point. When these two objects are given, we can then compute their distance. Because the iterative projection algorithm involves the sequential solution of multiple linear programs, its computation is not feasible for real-time applications. In our Python application implementation, for example, the computation time was approximately 10 milliseconds. Besides that, because of its multiple discontinuities in its gradient, the iterative projection is a non-differentiable function, and this prevents us from computing the gradient of the stability margin with respect to its input state lambda, which would be very convenient for trajectory optimization applications based on gradient descent. Based on these motivations, we decided to resort to a data-driven approach, and we tried to estimate the feasible region using a multi-layer perceptron. The benefit of this choice is twofold. Not only the MLP allows to drastically reduce the inference time when calling this function, but it's also a differentiable function that can be employed for nonlinear trajectory optimization. The input of this MLP is a minimal set of all the required quantities needed for the evaluation of the robot stability. This includes the unit vector EG, which represents the gravity orientation with respect to the base of the robot, the center of mass linear velocity and acceleration, the base angular acceleration, possible external branches, the possible external branches applied to the robot's base, the foothold locations, the friction coefficient, the contact states, and the contact normals. It is important to notice that the contact locations are expressed with respect to what we call the horizontal frame. This frame is placed in the center of mass of the robot, and it therefore implicitly carries the needed information about the relative position between the COM and the contacts. The network is obviously only reliable inside the range of parameters it has been trained with. Here on the right, I'm showing the set of distributions used to generate the training set. Using these parameters, the network minimizes the estimation error with respect to the analytical stability margin computed using the iterative projection algorithm. The neural network takes the current robot state as an input composed of the 47 scalars I mentioned before, and it predicts the value of the stability margin. We tried different implementation of MLPs, and we ended up using an architecture with 3 hidden layers of 256, 128, and 128 nodes each. The forward pass for our implementation of such a network is approximately 10 microseconds, which is about 3 orders of magnitude faster than the analytical computation. The vector of the margin gradient can be computed through backpropagation in approximately 100 microseconds. This is 4 orders of magnitude faster than the computation of the analytical gradient that could only be performed by finite differences. Here we show some of the estimation results that we obtained with this network. You can see here on the top row, for example, the learned stability margin values in the case of the robot standing on a flat surface with different stance conditions. 4 feet on the ground for the top row, the left hind foot in swing for the middle row, and the right hind foot in swing for the bottom row. As expected, the maximum value is obtained when the robot center of mass is located in the center of the support polygon, which corresponds to the origin of these plots. As the center of mass deviates from the center of the support polygon and therefore it gets closer to its edges, we can see that the learned stability margin also decreases as expected. We can show that in the range of states which is relevant for dynamic walk and trot, which is approximately plus and minus 15 centimeters from the origin, the estimation error between the analytical margin and its learned counterpart is always less than 1 centimeter. In this second plot, we can see that the stability margin, which is shown in the top row, and its gradient, which are in the middle and the bottom plot, we show how it changes for variable center of mass accelerations along the x and y directions. We can see that the gradient of the stability margin is smooth, and it does not show the discontinuities that can instead be found in the case of the analytical stability margin, which is shown in red. This is the main feature that allows us to safely employ the learned stability margin for nonlinear trajectory optimization and reinforcement learning. I will now demonstrate some of the results that we obtained in these domains. Here we show the first application of the learned stability margin in a reinforcement learning setting. In this case, the stability margin acts as a dense reward function that keeps the robot balanced while attempting to track a desired forward speed. These simulations show that even for a partially tuned policy like the one shown here, the resulting behavior exhibits a lower base acceleration compared to a policy trained without the stability margin reward. We also used the learned stability margin in the Harlock paper to train a terrain-aware footstep planning policy, a domain adaptive tracking policy, and an emergency recovery policy. In all of these cases, the learned stability margin acted as a dense reward function in order to maximize the robot's stability on rough terrain alongside the different primary tasks. As you can see in this video, the robot is able to achieve a dynamic trot on a rough terrain thanks to a wider stance of the footholds that comes as a direct consequence of the maximization of the stability margin reward. For more details about the RL policy and hardware results, please refer to the Harlock paper by my colleague Siddhant Gangapurwala. Secondly, we will now also demonstrate using this margin in a nonlinear trajectory optimization, where we can take advantage of the efficient computation of the gradients. What you see here is the result of an online nonlinear trajectory optimization that employs the learned stability margin as its only means to enforce dynamic consistency and feasibility. The optimization variables are the base pose, the base twist, and the foothold locations for each node of the discretized time horizon. The stability margin is enforced in the form of an inequality constraint. The other constraints limit the range of motion of the feet and make sure that the feet height always matches the terrain height during the stance phases. The initial state corresponds to the actual state of the robot, while the final state enforces the desired steady-state velocity. The formulation also includes a cost that penalizes the slope of the terrain in the foothold locations. In this way, the robot achieves stable contacts and the necessary clearance from the step required to negotiate the obstacles safely. The optimization formulation replans in a receding horizon fashion at 1 Hz, the center of mass trajectory and the contact locations, on rough terrains over an horizon of 3 seconds. It is important to notice that in this formulation we do not need to explicitly include the contact forces, as they are already considered by the stability margin. This allows us to achieve feasibility guarantees with less optimization variables compared to other force-based formulations. In these videos we can see the Animal C robot walking over different terrains. The color maps overlaid over the terrain show the corresponding value of the learned stability margin. The one on the top video shows the value of the stability margin if the robot was to place its foot in that location for all the other state parameters fixed. The color map on the bottom part of the screen instead shows the value of the stability margin if the robot was to place its center of mass above that location, having all the other parameters fixed. Based on such information, our motion planner is able to jointly optimize online the feet location and center of mass trajectory, like the ones shown on the terrains shown here. I would like to highlight that probably the main benefit of learning a stability measure based on the feasible region rather than based on any other possible criterion is that it also considers the joint torque limits. As a consequence, the motion planner avoids configurations that would be excessively torque intensive, such as when the legs are too retracted. In this scenario, shown in this video, for example, the robot keeps its base closer to the lower part of the lateral step and it enforces a small roll angle in order to optimize the overall manipulability of the robot. The same is captured by this simulation, where you can see a similar side step like the one shown in the previous video. The plot shown on the top part of the screen shows the feet and center of mass trajectory optimized using a standard force-based formulation. Because this lacks of any knowledge about the robot's joint torque limits and about the leg's manipulability, the robot tends to keep its base exactly in the middle between the right and left legs. This causes the left legs, the one on the step, to be excessively retracted. The trajectory shown in the bottom is obtained instead using the learned stability margin that we presented here. You can see that the robot tends to keep its base closer to the more retracted legs in order to ease the load from the legs which are in a less favorable configuration. In conclusion, I would like to summarize the main points of this work. First of all, we have proposed the usage of a stability metric that exploits the capture point and the feasible region in order to generate dynamic motions such as trot and walk in presence of rough terrains. We have also shown that how data-driven approaches can be used to efficiently estimate the stability margin and its gradient with respect to the input state. The resulting mathematical tool, we have applied it in a reinforcement learning scenario first and in a nonlinear trajectory optimization formulation. We have shown that in both cases the usage of the learned stability margin helps the robot find feasible trajectories that satisfy the motor limits, even when the contact forces are not explicitly optimized. That's all for my presentation. Thank you very much for your attention.